Hello again. This is our last lecture for the quarter, and we're going to discuss reduction of aromatic compounds. Okay, so let's say we're starting with styrene. So remember, styrene has a benzene ring and then a 2-carbon chain where a double bond exists between carbons 1 and 2. Now, if we were to just add one equivalent of hydrogen, that would only reduce the double bond on the carbon chain coming off of the ring. If we wanted to completely reduce the benzene ring, remember we would have to use 3 equivalents of hydrogen with a nickel catalyst and high pressure. And then we would end up with our with all single bonds on the ring. So that's one example of reduction that we could perform on a benzene ring or on a substituent on the benzene ring. But there's also a special kind of reduction that we can perform called a Birch reduction. All right, so this one's kind of interesting. So let's say you start with a benzene ring. You can add pure sodium, which remember, pure sodium is very reactive with water. So you don't want to have any water present during this reaction. Instead, you could use an alcohol like methanol and ammonia. So this is kind of similar to when we were turning a molecule into a transalkene, right? But this time, we're turning a benzene ring into the following. So here we have 2 double bonds, and they're on either side of the ring, so they're opposite each other. Okay, so this is not a conjugated system because we no longer have alternating double bonds and single bonds. Let's see. So let's look at the mechanism in a little more detail. And the mechanism will be pretty similar to our dissolving metal reduction, where we turned the alkyne into a transalkene. Okay, so let's start with our benzene ring. And we're going to start with our pure sodium metal. And remember, sodium has 1 valence electron that it can donate, and it will happily donate, so it can become more like an noble gas with 8 valence electrons. So let's just pick a carbon that it donates to, because they're all kind of the same there. So when that happens, we actually will cleave the double bond. And we form a new double bond on the side there. So this is kind of starting a chain reaction around the ring. All right, so then we end up with a lone pair of electrons at that top position where sodium added its electron. And now sodium is positively charged, so it can balance that negative charge. We still have our double bond on the right-hand side there, but we formed a new double bond on the left-hand side, and we have 1 electron hanging out at the bottom. So in the next step, we're going to add alcohol. And the lone pair on the top of the ring can grab the proton on the alcohol. And then we'll just leave the shared electrons behind. Okay, so now there's two hydrogens at the top position. So it's now neutral. Oops, sorry. And now we have to neutralize the bottom carbon. So sodium is going to come into play again. So another sodium atom will come in and donate its electron to the radical carbon. So now we have a negative charge on the bottom. So again, we can add more of our alcohol. And, oh, I keep hitting the wrong things. And then the lone pair will grab that hydrogen from the alcohol. We'll leave electrons behind on oxygen. And finally, we get our product. So this is a really cool mechanism. And this was studied by an Australian chemist named Arthur Birch, which is why it's called the Birch reduction. Okay, so let's talk about what type of products you would end up with if you had like an alkyl group attached, or maybe like a ketone or something attached to this benzene ring. Okay, so let's start with a ketone. All right, so let's say we have a ketone on the top of our ring system there. And we're going to add our reagents for the Birch reduction. So there are two products that we could end up with. So we could end up with a product where the ketone is kind of in the middle of those two double bonds, or we could end up with the ketone kind of bonded to one of those double bonds. So let's figure out which one is preferred, which one actually forms. Okay, so it really does depend on that group that's attached to the benzene ring and whether it donates electrons or withdraws electrons away from the ring. So in this case, we have that double bond to oxygen. So we could potentially draw electrons away from the ring through resonance. So that means our ketone is an electron withdrawing group. All right, so the carbon on the benzene ring, that really wants electrons because the electron group is pulling electrons away. Okay, so I'm just going to circle this ketone up above, and we'll label it EWG because it's an electron withdrawing group. So if the carbon on the ring now really wants electrons, that means it wants to be reduced. So it probably wants to increase its CH bonds, so it wants to gain a hydrogen, or decrease decrease its oxidation number. Okay, so let's actually calculate that carbon's oxidation number. What is its oxidation number there? So that carbon is only bonded to other carbons, right? It doesn't have any hydrogens or oxygens or anything attached to it. It's just bonded to other carbons. So that means it's sharing its electrons with those other carbons, which means its oxidation number is, let's see, so its valence electrons, it has 4, and then it's sharing electrons, so we would then subtract 4. And it has a double bond there, so if we drew a more detailed picture, again, it's completely sharing its electrons with those other carbons. So we would subtract those 4 electrons that it quote unquote owns, and that would give us a total of 0 for its oxidation number. Okay. So we want to make sure that we increase the number of carbon-hydrogen bonds at that point, or decrease the oxidation number, or do both at the same time. Okay, so let's look at our potential products. Let's look at the first product. And let's again look at that same carbon atom. What is the oxidation number of that carbon? So remember, there's a hidden hydrogen there. Okay, so let's draw a detailed picture. We've got a bond to carbon up above, bond to carbon off to the side, bond to hydrogen, and then a bond to another carbon. Okay, so in this case, carbon is completely sharing its electrons with the other carbons, but when we consider hydrogen, carbon is more electronegative. So it's going to take ownership of both of those shared electrons. So now we have 4 minus 5, which gives us an oxidation number of -1. Okay, so we've decreased the oxidation number. It's less than 0. We've also reduced that carbon by adding a hydrogen, so that is probably the preferred product, but let's double check the other product just to make sure. All right, so let's look at our carbon here. What is the oxidation number of that carbon? So I'm going to draw our Lewis structure again around that carbon. This time we don't have any hydrogens there, right? We just have a double bond off to the side with another carbon. So this looks pretty similar to our starting material, right? The carbon is completely sharing its electrons with the other carbons, so this would give us an oxidation number of 0. So in the second product, we have not increased the number of carbon-hydrogen bonds, and we have not decreased the oxidation number. So that second product is actually not observed, and it actually won't form. The other product, however, that is going to be our only product there. So again, in this reaction, we did a Birch reduction, And we saw that we could potentially have two products. There were two potential outcomes here. But because we had an electron withdrawing group, the carbon attached to that electron withdrawing group really wanted to gain some electrons back. So we needed a product where the carbon had a lower oxidation number than it started with, or gained a hydrogen. And we saw that with our product, we did both. So that's how we can determine which product will preferentially form. So let's look at another scenario. Let's say instead of an electron withdrawing group, we have an electron donating group. Let's see. So let's look at this molecule here. So we've got an oxygen bonded to a methyl group. And we want to do a Birch reduction. And again, there's two possible outcomes. So the double bonds could be on the left and the right with OMe in the middle, or we could potentially have the double bonds kind of at the top and bottom, and OMe is bonded to one of those double bonds. Okay, so again, in this situation, if we look at our resonance structures, that oxygen can donate electrons into the ring. So it can give electrons to that carbon it's bonded to. So this is actually an electron donating group. Oh, sorry. So electrons can donate into the ring. So we have an electron donating group. So we'll abbreviate that EDG. Okay, so that means that the carbon bonded to the EDG does not want electrons because it already has electrons. Which means that it would want to be oxidized or maintain its oxidation number. Okay, so let's figure out what the oxidation number of that carbon is. So this time, the carbon that we're referring to is bonded to an oxygen up above. Oops, sorry. And then it's bonded to a carbon off to the right and double bonded to a carbon off to the left. So that carbon is sharing its electrons with the other carbons, but would it have any ownership over the shared electrons to oxygen? No, right? Because oxygen is more electronegative, so oxygen would have full ownership of those electrons, at least when we're calculating oxidation numbers. All right, so this would be, let's see, we have 4 valence electrons minus the 3 electrons that carbon has ownership of. So that means we have an oxidation number of positive 1. Okay, so in our product, we want to maintain that oxidation number or increase it. Okay. So now let's look at our two potential products here and figure out which one is preferred. And again, we're going to look at that same carbon and figure out its oxidation number. So in our first potential product, what is the oxidation number of that carbon? So remember, there's a hydrogen in there. Carbon has to have 4 bonds total. So right away, we can tell that that carbon has been reduced because we've added a hydrogen to it. But let's still calculate the oxidation number. Okay, so carbon in this situation, again, completely shares its electrons with the other carbons. So it has ownership of half of those. It does not have ownership over its shared electrons with oxygen. And then we said previously that carbon would have full ownership of its shared electrons with hydrogen. So it owns a total of 4 electrons, so its oxidation number is 0. So that means its oxidation number has decreased, which is the opposite of what we want to happen in this situation. So that tells me that this first product we drew is not our preferred product. But let's just double check the second product and make sure that that is the preferred product. All right, so let's calculate the oxidation number for that carbon. All right, so again, we have a carbon bonded to oxygen, another carbon, and then it has a double bond to another carbon. So this looks a lot like our first starting material situation, right? So carbon does not have ownership of its shared electrons with oxygen, but it does have half ownership over the electrons it shares with other carbons. So that would be 4 minus 3, which is positive 1. So that means we have maintained the oxidation number of carbon in that second product, which is what we want. All right, so that second product is our preferred product. And the first potential product is not observed. Okay, so again, on this problem, we saw that the substituent on the benzene ring could donate electrons into the ring. So the carbon that it's bonded to actually has enough electrons. It does not want any more electrons because electrons are being donated towards it. So it actually wants to either maintain its oxidation number or increase its oxidation number. So we saw that out of the two potential products, the second one was the preferred product because the oxidation number was maintained. Okay, so hopefully this made sense. If you have any questions, feel free to set up an office hour with me or feel free to message me or email me.